All right, welcome back for another episode of Con E 352. This time we're going to be talking about larger cooling equipment, chillers, both air-cooled and water-cooled, and cooling towers. All right, bigger equipment. We've already talked about like the basic ones, you know, like residential size stuff, the stuff that fits through a window, or maybe the split system that is just for one single house. And even kind of similarly, simple rooftop units. All of those are kind of like smaller equipment, good for one residence, one office, one house. The rooftop equipment, that's good for like one zone, like a gymnasium, something along those lines. Maybe even an open office space where you have a bunch of open cubicles, but really it's just one big room. Once we get into multiple rooms with multiple different cooling profiles, things get more complicated. And that's where we need to increase the sophistication of our cooling system. And I mean, think about this. In a house, you get one thermostat. You locate the thermostat in the center of the house somewhere, and you just get what you get. In other words, I'm going to set that controller for my desired temperature, but I know that if I go upstairs, it might be a little bit warmer, and if I go downstairs, it might be a little bit cooler. And if I want a different temperature in one of those other spaces, I'm going to have to maybe turn down the thermostat or turn up the thermostat where it's at. And you just kind of know how to do that within your own house. You can't do that in a building, let's say a building the size of Town Engineering. You can't just have one thermostat. And you can't just have one temperature for every space. Different spaces are going to have different cooling demands. They're going to change constantly. Let's just look at a classroom space like a Town Engineering. We might have an office that has one person in it. But maybe the office on the east side of the building, when the sun comes up in the morning, it gets warmer sooner. And then in the afternoon, that's when the south-facing offices get warmer or the west-facing offices get warmer. Maybe on a classroom, one classroom is full at 8 o'clock in the morning and it actually needs cooling, whereas some of the other rooms don't have anyone in it yet. So as people come in and out, lights get turned on and off. You know, conference rooms might be empty 1 minute, full the next minute. All of those, both internal and external loads, are going to change the temperature within each individual space. So some will need cooling, some will need a lot of cooling, some will need a little bit of cooling. We're going to have our air handlers produce 55-degree air all the time, but we're going to have to reheat some of that air at each individual space. How do you do that? Well, that's where we get into variable volume systems, and we looked at this in Con E 251, if you remember. The variable volume systems like at the DMAC project. When we looked at the mechanical sheet metal drawings, there's a box for each space that allows varying amounts of cool air into that space. It controls the temperature that way. We can't do that with a simple split air conditioner like you would on a house. We need bigger stuff. Also, for a bigger building, we might have multiple air handlers for one large building. So I need to be able to cool all of those individually. Once again, we're going to need some bigger and more complicated equipment. And that's what this discussion today is. Let's first, if you remember the basic parts of the refrigeration cycle, you'll be able to look at any size piece of equipment and just think of it in these basic parts. Where's the compressor? Where's the condenser? Where's the evaporator? In other words, where is it removing heat from? What is it making cold? And then where is it rejecting that heat? Where is it getting rid of it to the outside? So far, we've always talked about on the other side of these two heat exchangers, there being air. On the evaporator, it's room air, return air. And then on the condenser, it's outside, it's ambient air. But we don't always have to do that. We could, and this is where we get into something called chillers. We could, instead of heating the air, instead of cooling the air directly, we could make chilled water and then take that chilled water probably down around 40 degrees, give or take, and send it to cooling coils within an air handler. And the advantage that we get, well, we get several advantages when we start to do that. One of them is efficiency. It is more efficient to transfer energy in and out of water than it is air. Our evaporator coil can be smaller. We can also do the same thing on the condenser side. Instead of ambient air that we pass over it, we could pass water across it. And I'm going to give some examples of each of those. So just stand by for that as we strive to increase the capacity, not just the size, but the capability of our systems. They're going to get progressively more and more and more complicated. So get the handout, the notes packet for section 2. I'm on page 13, and if you follow along, it'll make it that much easier to understand. All right, and we've already gone through this, all the different pictures. The picture on page 13 is a gas-driven one. Don't worry about this one all that much. All right, so I'm not going to test you on it. It exists. They're kind of rare, where we use natural gas to actually turn a refrigerant compressor. But let's just skip that one. All right, and let's go down. Here we go. This is an example of a schematic, and I've got pictures of the real things, but this is just a schematic of a water-cooled chiller. A water-cooled chiller. These are going to be the biggest ones. These are going to be the ones with the largest capacity. It's going to make chilled water. Water is going to come back from an air handler, go through the evaporator, and now it's cooled down. It is chilled. We're going to take that water, take it to an air handler, and make air conditioning with it. Now, the advantage here is instead of putting this evaporator directly in Airstream, I can put the refrigeration cycle anywhere I want it now. At Iowa State, these big chillers are all the way down across campus over at the physical plant. They're a long ways away from the schools. What that means is by using a chiller, I've separated the refrigeration cycle from my occupied buildings. The maintenance is easier in some ways than, say, our smaller systems, because now we can put these chillers wherever we want it, maybe in a mechanical room. We can put it out of the way so we don't see them. That's one advantage of this. All right, we can do the maintenance in an area that's easier to access if we plan this out right. So there's a lot of advantages to doing it with these bigger units. Okay. Also, in terms of energy efficiency, these are the largest ones in terms of physical size and cooling capacity. They're also the most efficient. If we define efficiency as kilowatts of energy used, kW, per ton of cooling, these bigger ones are going to be the most efficient. I'm transferring energy through an evaporator that is cooled by water. We're also going to have water at the other end here on the condenser side. I'm going to explain that in a little bit. These large compressors can now be variable frequency drive driven. Remember, the variable frequency drives, as they speed up and slow down, the variable frequency drive uses the flow rate varies with the speed. In other words, if I'm turning a motor half speed, I'm getting half flow. Whether that is for a pump, a fan, or a compressor, those laws hold pretty solid. We're ignoring some drive losses, but just bear with me. About half speed is about half flow. Flow varies with the speed of the motor. Power consumption, though, varies by the cube. In other words, if I am at half speed, you take that cubed, I am only using 1/8 of the power. That is a huge energy savings. And that is why, for a lot of our motor-driven equipment, we're going to have a variable frequency drive on there. It's a good way to control flow rate, but it is a great way to save energy. That's only really practical for the larger motors because of the first cost of the variable frequency drive and the complexity therein. So you're not going to find these on like residential size equipment. This is bigger stuff. But having a variable frequency drive on it makes it much more efficient. So when we put these down at like a physical plant on the other side of campus, we can put all of this stuff that requires maintenance there as well. And then a cooling tower for our big chillers. We're going to reject heat to the outside. We're going to pump condenser water through the condenser and to a cooling tower. And that is going to reject heat to the outside. A cooling tower is basically just a big open tube, if you will. We're going to dump water through it and blow air across it. I've got some pictures here in a second. By doing that, a small fraction of that water evaporates. And just like sweat evaporating off of your body cools you down, a little bit of water evaporating out of this airstream removes a whole bunch of energy. So the cooling tower rejects heat to the outside that way. And once again, that's about as efficient of a way to do it as is possible. All right, let's look at some pictures. I think some pictures will help. All right, first, let's talk small systems. The simple window air conditioner is an example of a unitary packaged equipment. Unitary packaged, it's all together, it's all one piece. You go to Walmart, Sam's Club, Lowe's, I buy a window air conditioner. Everything I need is right there. I just have to plug it in. I have to go to a window. Notice, this is inside the building, outside the building. The evaporator faces inside. If you put the window air conditioner into the wall, the part that's facing you is the evaporator. It's what makes things cold. Room air comes in, passes through the evaporator, and then blows out. You stand in front of it, you get that cold air. On the outside is the condenser. That's outside air, blows across it. And then the compressor and thermal expansion valve and all the piping is all inside this box. This is a window air conditioner, unitary packaged. One time, here years ago, when I was a freshman, I unfortunately was put in the Towers dorms. And in Towers, you could not have an air conditioner. And that particular August, like most Augusts in Iowa, is brutally hot. Can't have a window air conditioner. One student thought he was going to be smart. He was going to show them. He actually brought a window air conditioner and thought, all right, I'm going to run this and I'm going to show them. I'm just going to set this on my desk and I'm going to turn it on. And so he put it on his desk, he turned it on, and then he left for class. He thought, by the time I get back, it's going to have my room all nice and cool. No, it didn't. By the time he got back, it was like 120 degrees in his room. By setting this packaged unit inside, there's no way to reject heat outside. The air conditioning system, the refrigeration cycle, has to reject heat to the outside. So on every system that we see, whether it's the simple through-the-wall unit or the big chiller, something important to ask yourself, where is the heat being rejected to the outside? All right, advantages of this system. It's simple. Installation is easy. There's almost no know-how. You open a window, you put it in, you close the window down, you turn it on. There, you're done. Nice part is I've got my cooling system exactly where I want it. In other words, I could have multiples of these. If you had a house, you could put one in one bedroom, one in another bedroom. Everybody gets to control their own temperature. Downsides of these units: they're noisy, they're loud. You are putting the compressor and the fan and everything that makes noise right at the room level. Other downsides: they don't get all that big. You might have to have a couple of them for a really big room. For a house, you would have to have several of them. Not terribly handy way to do that. Other downsides: you see them. They're right in the window. You see it from the outside, you see it from the inside. It's ugly. Nobody likes that. So there's a lot of downsides to this. Simplicity is the advantage. Appearance, noise, and aesthetics for sure downsides. And in terms of efficiency, kilowatts of electricity used versus net cooling effect, this is going to be one of the worst efficiencies. In general, the smaller systems have lower efficiencies than the bigger ones. All right, let's keep going. All right. I'm going to keep on turning through the notes. I do want you to read all that good stuff, but I'm on page 23. A step up, the residential unit that we've already discussed a lot. Advantages. Now I've got the compressor outside. I can put it wherever I want, and I pipe refrigerant between the two halves. Usually, I hide the inside part too. No, you put the ductwork in the basement in places you can't see it. You put the furnace and the fan section in places that you can't see it. I get a little bit bigger capacity. Whereas the through-the-wall unit is usually 2 tons or smaller, these units can be up to about 5 tons worth of capacity. Downside, they're a little bit more efficient, but definitely not the best efficiency choice. Downsides are it's limited in capacity. Even a house, a really big house, might have a couple of these. All right, so let's keep on turning. Rooftop systems. Think anywhere from 3 tons to 150 tons of capacity. Lots of different manufacturers make these. Trane, Lennox, York, Carrier, McQuay, bunches of different ones. Rooftop units. Up on the top of the roof. They're out of the way. You can't see them, and they don't take up space inside the building. Now, downsides. Most rooftop units, the simple ones, the ones that have the same controls as the residential unit, you basically get one zone of control. It's on or it's off. Maintenance is on the roof. Makes it difficult. Because the equipment is outside, you get a reduced life expectancy, probably no more than 15 years. Right? Because they're outside and on the roof, they have a tendency to leak. I don't mean leak refrigerant. I'm talking about leaking like at the roof, water. Here's some pictures of some rooftop units. Right? Notice they've got to be flashed to the roof. That's what I'm talking about, is where they sit on the roof requires structural support. And it's also an area of concern when it comes to leaking inside the building itself. A lot of buildings will have rooftop units. Now, I've got some pictures here. These are the simple ones. Let me get to some complicated ones. Oh, I don't. All right. Maybe those pictures are later. Here. The bigger rooftop units can have variable frequency drives on them, on the supply fans. You can pair them with variable air volume boxes, VAV boxes. So once you get into bigger and bigger capacities for those rooftop units, we can get more features on it and therefore get more zones of control. And like I said, they go up to 150 tons. A few manufacturers make some that are even larger than that. But once you start getting really, really large, you'll probably want to go the chiller route. Let's talk first. I'm on page 28. An air-cooled chiller. So I take a chiller and I sit it outside, like the one at DMAC, at the Hunziker Career Academy. I'm going to sit that thing outside. I'm going to make chilled water, and I'm going to pump that chilled water into the building. Now, there's some good advantages to this. I put the refrigeration cycle, the compressor and the thing that makes a lot of noise, I put it outside. That's good. I don't take up any space within the building for that refrigeration cycle. That's also good. If I put it at grade, like the one at DMAC, it's easy to get to. Maintenance is a little bit easier than putting things up on the roof, and that's also an advantage. However, it is still outside, so that big chiller probably only has a life expectancy, once again, of 15 years or less. All right, that's not all that awesome of life expectancy. The water-cooled ones will have longer life expectancy, and I'll explain why when we get there. But one of the advantages is I can have one chiller and supply chilled water to either one big air handler or dozens, hundreds of smaller air handlers. I get more flexibility on the inside of the building where I put my air handlers with the chiller. All right. Now, it still does generate noise. That's still a downside. You're putting that noise-producing thing outside. Sometimes it has been known to upset neighbors if they're really loud. So just be cautious of where you put it. Most likely, the cooling capacity for an air-cooled chiller is probably in 50 tons and up to 300 tons. Some vendors make some even a little bit bigger than 300 tons. In all honesty, once you get above 200 tons or so, probably want to start looking at a water-cooled machine, which are the biggest ones. Let's take a look at an air-cooled one. Here's a picture of an air-cooled chiller. Right, compressor down below, condenser coils up here. These round parts on the top, those are fans that blow air across these coils. The evaporator is right here, this barrel. That is where we're going to make chilled water, and then we're going to pipe that chilled water into the building for use there. Here's another, just different vendors, different sizes of air-cooled chillers. Now let's get into water-cooled chillers, the big ones with the cooling tower that I was talking about earlier. The chiller part, the compressor, the evaporator, the condenser, that whole big piece of equipment is actually located inside of the building somewhere. We have to pipe condenser water outside to a cooling tower. Because of this, we added a lot of complexity compared to the air-cooled chiller. The advantage is by putting this equipment inside, it is going to last longer. For a water-cooled chiller, you should expect that to last 20 or 30 years, maybe even longer with good maintenance. I've seen some chillers last 40 years, actually, with really good maintenance, which is pretty impressive for any cooling equipment. These come in capacities up to like 3,000 tons worth of capacity. Iowa State has 3 of them that are almost at 3,000 tons. And remember back to our picture with the horse cart of ice, that is a lot of ice. That is a lot of ice. All right. So big advantage, life expectancy. Big advantage, energy efficiency. Big advantage, I have one big compressor to do the maintenance on instead of, if I need the same capacity, if you had that type of need and you were going to do it with like small rooftop units, you could end up with dozens, hundreds of rooftop units to get the same total cooling capacity as one really, really large water-cooled chiller. So the question is, do I want to do maintenance on one big machine, although very complicated, versus a bunch of smaller machines? Even though they were simpler, each machine would be a little bit on the more simple side. All right. Another downside, I've added an extra step, which is a cooling tower. So now I've got to do extra maintenance on the cooling tower. And let me take a look at that. All right. Here are some pictures of some water-cooled machines. I'll just let you take a look at them. I've got some like, actually, here we go. I can't remember if that's from a project I did. That looks like one of the projects I actually designed, but I could be wrong on that. All right. This is a water-cooled chiller. See these circular parts? One of them is the evaporator barrel. One of them is the condenser barrel. The part on top is the compressor. That's also where the thermal expansion device, or rather the orifice for a big machine, is going to be. This big flat panel here, that's the power input to the compressor. On a very large one, we'll have that variable frequency drive on it. We're going to need pumps. These are chiller pumps, pumping water from the chiller to the air handlers and back. We're also going to need cooling tower pumps, right? And cooling towers. Here are some pictures of cooling towers. I'm on page 37 of your handout. Cooling towers are used to reject heat to the atmosphere. They pass water through this. Take a look at this picture, right, on your computer or print it out. You'll see this black stuff in here. This is like a black fill material that they put, the water goes through that. All right, kind of like a swamp cooler kind of a thing. The water just kind of goes back and forth in there. And then the air is drawn across this with a fan. Let me get a different picture of a different style. Here we go. Here's another style. This is a Marley cooling tower, I think. Once again, water comes down through here. It draws air across that. Some of that air evaporates, and it's that causes the cooling effect and rejects heat to the atmosphere. Right? Just a different style. The big circular parts up at the top, that's actually where the air is pulled through. All right, now, something important here. If we're taking ambient air and pulling it across here, it's exchanging energy with that air. It's actually in contact with the air. The ambient air is actually in contact with the condenser water that passes through the condenser side of that water-cooled chiller. The downside of it is that water, while doing a very good job of exchanging energy, is also a really good mechanism for cleaning that air. Any dirt, any dust, any pollen, any leaves, any small birds or insects, any seeds, anything, organic matter that is in that airstream will get caught within this cooling tower. So it requires a lot of cleaning. It requires additives to this water like biocides to prevent bacteria from growing in it. The cooling tower fill media itself will need power washed and cleaned occasionally to get rid of that stuff that gets stuck in there. Cooling towers mean extra maintenance, but they also mean overall a better system. It's much cheaper just to replace these than it is the entire system. And if you think back to here, if we go if we go to downtown Des Moines and we look at some of those projects that I had pulled up here earlier, we go into downtown Des Moines and we look at, let's see here. All right, what I did is I pulled up Google Earth for the Des Moines metro area. I've got a little marker right there on 801 Grand, kind of give you some bearings. And why don't you do the same thing? Go to Google Earth and look there, and I think it'll be easier to follow along. If we zoom in on the Des Moines area, I want to talk about a couple of different chiller plants that I worked on that I've already talked a little bit about, but let's go into a few more details. This is the Nationwide Insurance Agency, their corporate headquarters, or one of their corporate headquarters. Going back over here, right here to their parking ramp across the street to the south, this is their parking ramp, and right here are their 3 cooling towers for their chiller plant. I designed the chiller plant, and it is in the parking ramp right there. If we look, there we go. If we look right there, their chiller plant is right behind that door. These two are the generators. This is the boiler room. And if you go in that door, you'll see the chiller, and then above it, up here, are their cooling towers. Now, why this is pretty awesome from the perspective of a cooling plant is they put their chillers and their whole cooling plant away from their office space. They have the expensive space, which is the office space, and then they have the parking ramp. The parking ramp is obviously much cheaper, dollars per square foot. The maintenance for these are easy. This is a big overhead door. I can just drive right in with a truck. The cooling towers need maintenance. I can just drive a service truck up to beside them and just go right to them there. Makes this really, really easy. Their air handlers are over here on top of their building. They're encased in these penthouses right here. The way that we get chilled water and heating water over to that building is actually underneath their skywalk. It's in the skywalk, but it's below where people walk. So this makes just an ideal place for a cooling tower. Now, they have a chiller because it allows them to put it all the way over here. They went with an air-cooled chiller because of the massive capacity of this particular plant. Right? Now, if we compare this plant to this other one that I did right here. Wells Fargo Home Mortgage. The cooling towers are right there in the center. The chiller is right underneath them in a mechanical mezzanine. Same idea, water-cooled chiller with cooling towers. However, this one, they did not own their own parking ramp. They had to put them on the building and hide them somewhere. So they put them up there. This will be a lot more difficult to replace when the time comes. Don't even know how you would end up. You'd end up needing a tower crane that would have to be built. Maybe I'm not even sure where. However, they bought the best cooling towers that money could buy, knowing that this would be very difficult to replace. However, it's still going to need replaced someday. They put it off for as long as they could, but someday this is going to be pretty difficult to do. And if we go through the downtown area, you'll see this again and again. Cooling towers kind of hidden on top of a large building. Now, I'm going to go over to another plant I know a little bit about right here. Principal Financial owns this building, this building, this building, this building, and they own 801 Grand, but 801 Grand is on its own system. The cooling towers for all of this are right here, and the chillers are down in the basement of this building, and they're also down in the basement of this building. There's tunnels that go underneath the streets in all the way around there that connect all of those buildings together, and that's where they put their chilled water plant. And plants, I should say it's plural, plants, and also it's where they put all the piping that goes from one to the other to the other. All right, now let's zoom out a little bit. Go a little bit north. We'll go to Ankeny. And we'll go to the DMACC campus right here. State of Iowa Hygienics Lab, Medical Examiner, Crime Lab. The chiller plant for this is underneath here in the basement, and then the condenser water is piped out to some cooling towers across the parking lot out here. Notice a common theme here. Very frequently, when I need remotely located things, which is very common. You only got so much space on any site. The advantage of the systems where I'm pumping water around from spot to spot is that I can put that stuff basically anywhere. Oh, also, just as a side note. Oops, that's the hygienics lab. Here we go. Right there. That is a skylight, and this is the main autopsy suite. If you die suspiciously, I know where you're going to be looked at. All right, let's zoom out. Let's go to Ames for just a second. If we go to Iowa State and we go to the physical plant, it has a power plant that produces electricity, of course, but also in this complex are a bunch of, well, I'm sorry, the complex itself is right here. Okay, I want to say these are the gas-fired, and then the chiller plant is over here, and I think that's the coal-fired part. But all of the heat from this is rejected right here, this massive string of cooling towers right along there. And at one point, Iowa State was running out of cooling capacity, and instead of make that system bigger, they decided to add a second cooling plant and connect the two over here. And actually, this was done. The project manager for this project was an Iowa State alumni, mechanical emphasis, Connie. And I want to say that this picture was taken while they were still working on this. So the chillers are in there, and then those three are cooling towers right there. All right. Now, if we go to, just for a little refresher, if we were to look at the Hunsaker Center, smaller cooling capacity. But if you remember, that air-cooled chiller sitting right outside, right there. Okay, it's close to the building, right, which is not always desirable, but that's a shop area, so maybe it's not such a bad thing. Those do produce noise, so anybody that's going to build right here would know, but they were there first. So there you are. All right. So different capacities, different systems, different relative advantages and disadvantages. Every time that we kind of go up the scale, we increase complexity and we increase costs for sure, but we also increase efficiency. And once we move all the stuff inside, we're going to have a lot longer life expectancy. All right, so let's pause there. The exam is Thursday. I'm gonna post a notice for the exam here in just a few minutes. Probably see the notice for the exam before you see this lecture video. And next week I'm gonna save the heat pump lab, or I'm sorry, the heat pump lecture. Might do it next week. We'll see how tomorrow goes. All right, which means I'm just a little bit behind, but we're still on track for the next exam. So good luck on the exam, and I will see you later.